Okay, chemistry time. We're going to try to call this one electron configuration again with the hopes that we will actually talk about how to do electron configuration today. Electron configuration again. We did get time to talk yesterday about the general format for electron configuration, which is something like, and these are the examples that we had up yesterday. We had the hydrogen is 1s1 and helium is 1s2. Yes? So far, so good. I want you to look with me at the Aufbau diagram. In your book, it's on page 156. If you're watching this only on a video, it's this. You can kind of pause it. Copyright Glencoe 2008 or something like that. Citing my source. But this is the Aufbau diagram. I'm talking about this little kind of rainbow-colored diagram here on page 156. I'm going to draw a pretty rudimentary facsimile of it up here. What does the arrow on the left say? What is my y-axis here? Both of those, yep. I'm going to put energy increasing as we go up. Of course, that's what, if I just label it energy as we go up, that means increasing. And then it is also, as Rhett points out, that is the direction in which we fill the orbitals. So we have these options, not even options. We have a 1s orbital, 2s orbital, then slightly higher energy, we have 3 boxes for the 2p orbital. Then we have a 3s orbital. Slightly higher, we have 3 boxes for the 3p orbital. We have a 4s orbital. And then we have over here 5 boxes for a 3d orbital. And we're going to stop there on the board. There are more than that, of course, it goes up. Aufbau, if I remember correctly, is the German word for something like underneath the lowest or fill the lowest or something like that. It has to do with the fact that we fill these from the bottom up. The Aufbau principle, and you should write this down somewhere, but the Aufbau principle, which relates to this Aufbau diagram, the Aufbau principle is that electrons in their ground state occupy the lowest energy orbital they can. That's our first rule for solving electron configuration. Electrons in their ground state occupy the lowest energy orbital they can. What might ground state mean? No, not neutral. Electrons are never neutral. No. Well, how else could they be? What else can happen to electrons that we have discussed before very recently that might cause them not to be in their ground state, if you had to guess? Okay, how would they get more energy? What do we call that for electrons? Remember, we had the example of the flame test. How would we give the electrons of a given atom more energy? In the flame test, we put it in a fire where there's energy there, and those electrons absorb that energy, and they become, the word I'm looking for is they become what? When they absorb energy and they move to a higher energy level. You remember what that's called? It's just like if you have cocaine for lunch and it makes you really... No. Excited. I'm saying... Don't talk about cocaine in the school video, for crying out loud. But if you get, let's use something a little bit more appropriate. If you're real excited because, I don't know, your mom made enchiladas for lunch, or you're going to Disneyland, or you got a new Lego set, or you got a new car, or you just got your learner's permit, or whatever, or you just had lunch with your teammate mentor, you're really excited and you cannot sit still. Some of you cannot sit still. You wiggle around and you're in an excited state. It's the same with electrons. When they are given energy, they move to a higher energy level. But if they haven't been given energy, we call that their ground state. I'm going to put here unexcited. Unexcited. If they're unexcited, when they are not excited, when they are not given the energy needed to get to a higher level, they occupy the lowest energy orbital they can. So, and we are always talking about, in fact, we're going to go back a couple steps here, but we usually, if we're being very specific, if we aren't being very specific, we call this electron configuration. If we're being very specific, we call it ground state electron configuration. I've only ever seen these done for an atom in which all of its electrons are in their ground state. I guess it would be theoretically possible to do them for an excited state, but that really just isn't done. We call it ground state electron configuration, and we're always doing it for the ground state, which follows the Aufbau principle, that they occupy the lowest energy orbital they can. These are suborbitals. Each little box is a suborbital. Each little box is a suborbital. What's just a regular orbital? Well, the number here indicates the orbital. Remember, we had this yesterday. The number indicates the orbital. What does this little shape, sorry, I almost gave it away. What does the little letter represent? Shape, the shape of the suborbital. And then when we go to actually write the configuration out, this number represents, it's a little exponent. And we do not, just so you know, yeah, the number of electrons. And just so you know, we never ever, one real, like a little cheat code for me to know if someone doesn't have a good grasp on this is if they say 1s squared. This is not an exponent. It's a superscript, but it is not an exponent. It's not an exponent, and it's not a charge in the way that we have charges on our polyatomic ions. We pronounce this 1s2. I'm going to write that over here. We say 1s2. That's how you pronounce this. 1s2. Meaning, orbital number 1, shape S, there are 2 electrons in that, and that's for helium. Okay, and then the rule is, we're going to talk about more rules in a second, but this rule tells us that for any given atom, we just start cramming in electrons, which we indicate with arrows, into these boxes from the ground up. From the ground up, that's the Aufbau principle. Another rule is the Pauli exclusion principle. The Pauli exclusion principle. The Pauli exclusion principle tells us that only one electron of each spin, one electron of each spin may occupy each suborbital. I'm going to be more specific here. Only one electron of each spin may occupy each suborbital. What are the spins of an electron? I'm going to tell you. Up and down. Those are the 2 spins of an electron. An electron can either be spinning up or it can be spinning down. I'm going to make something up here, but I bet it's true. Remember how we said electrons can be fashioned as, or can be thought of as a wave? If we think of this as 2 electrons, one up and one down, you cannot have a wave that is 2 crests. That doesn't exist. In fact, I have a quote from Alan Watts on my board that says, you can't have a wave that is all crest and no trough. I have that up there to mean things like, you can't have a life that is all good days and no bad days. Otherwise, your good days are meaningless. But this means, in nature, you cannot have a wave that, in fact, even if we just draw this, there is a trough. That's, by definition, a trough. We can't have just crests. In the same way, we can't have only upspin electrons. We have up and down spin electrons. You have good days and bad days. That's a little like poetic metaphor that we're using. But this is true in nature. We can only have an upspin and a downspin electron. So we have to have, that relates to the next rule, Hund's rule, which is, ran out of room. I'll just do it up here. This is messy. Hund's rule. These are in no specific order anyway, so it doesn't really matter. Aufbau principle is probably the most basic, but they aren't in really any specific order. The Hund's rule is that electrons of one spin occupy each suborbital in an orbital before any of the other spin. I just barely had enough room. And I'll show you an example. We'll apply all of these. So we kind of, the most basic way to do this is to fill this chart in. Sorry. Electrons of one spin occupy each suborbital in an orbital before any of the other spin. So for instance, this p orbital will have all up spinning electrons before it has any down spinning electrons.
Say electrons
Of. So for a given element, we go to fill this in. Okay, let's just pick one. Pick one kind of near the top. Let's say, well, it'll have to definitely be before 30. So pick some element from 1 to 30. Fluorine. Fluorine. Good, let's do fluorine. F. F in the group chat. F, how many electrons does it have? The atom of fluorine. Why do I specify atom, just as a review? What else might it be that would change how many elements it has? Or sorry, change how many electrons it has? No. I'm going to have to pause it. Right, you can. Action. Why do I specify an atom of fluorine? What is true of an atom? What is true of an atom? What must an atom have? Remember, we had ions that can be different, but atoms must have what? They must do what, though? The protons and electrons must be equal. They must be equal. So if I say an atom of fluorine, how many electrons does it have, and how do you know? 9. 9 electrons. It must be the same as its number of protons because it's an atom, and the number of protons must be 9 because it's the same as the atomic number. So we're going to put in 9 electrons. So according to the Pauli exclusion principle, where do I put the electrons? Well, we start with the lowest energy orbital they can. What's the this is empty right now. What's the lowest energy orbital it can? 1s. So I put in an upspin electron in 1s. That's 1 down. I've got 8 more to go. Where do I put the next one?
You have to write that for all.
We're going to get to an easier way, but this is the basics of it. Yes, thank you for the question. This is true for all of them, but you don't have to draw this chart for all of them, certainly. We're going to get to an easier way to do it. I'm just explaining the fundamentals right now. Thank you for the question. No, we have to put in a downspin electron into 1s. 2, remember the Pauli exclusion principle. Only 1 electron of each spin may occupy each suborbital. And that, coupled with the Aufbau principle, means that we have to put a downspin electron in 1s before we can put anything in 2s. Okay, 2 down, we have 7 more to go. Where do I put the third electron? 2s. Next one? Down in 2s. We get to the p. P has 3 suborbitals. Remember, if you remember from yesterday, the suborbitals are x-axis suborbital, y-axis suborbital, and then this dotted line represents that it should be 3-dimensionally coming out of the board. So there are 3 different dumbbells here that make up the p orbitals, the 2p orbital. So energy level 2, the shape is p, dumbbell, and we're going to have how many electrons? Well, we put in 1, 2, 3. We're at now a total of 1, 2, 3, 4, 5, 6, 7, 8, 9. But did you see I had to put in 3 up-spinning electrons before I put in any down-spinning electrons because Hund's rule. Electrons of one spin occupy each suborbital in an orbital before any of the other spin. Okay? So then, using this as a tool, and this is true, but using this as a tool, we can write fluorine's electron configuration. Fluorine's is, in the same way that helium's was 1s1, fluorine's is what? Well, let's go through them all. 1s2, 2s2, 2p, how many? How many total electrons are there in 2p? No? 5. 2p, 5. 1s2, 2s2, 2p, 5. This is what we call the ground state electron configuration. This is the answer. So on your worksheet, it'll say fluorine. The answer is 1s2, 2s2, 2p5. No, I'll get to that in a second. How do we do it if we aren't going to do the chart in every one? Is that what you're going to ask, Tiana?
No, I was going to ask if we're doing it backwards, so it like gives us.
We'll get to that in a second too. I had something to say, and I thought it was important. And what was it? That would be nice, wouldn't it? 1s2, 2s2, 2p5. What was it? Oh, here's the nice way that we can check it. Can you think of a nice way we can check it? Yeah, add up all the electrons. How many are there in 2p? 5. How many in 2s? So far we're at 7. How many in 1s? 2, 9. Is 9 electrons the right number? Yeah. So we've checked to make sure it's right. Also, here as a little side note, and also something that's really important for us to, as we go forward, well, I already did it, but why did I highlight these? What's true of both of these? Yeah, they're both in energy level 2. And what's for fluorine specifically, and some other elements, but not all of them, for fluorine specifically, what's true of energy level 2? That's always very important in chemistry. It's the highest number here. We have a 1 orbital and we have a 2 orbital. What's very special about the highest orbital in chemistry? Yes, there can only be 8, and we call those electrons, they have a special name, valence electrons. Valence electrons. Valence electrons. How many valence electrons does fluorine have? Yeah. How did you know that? You just guessed? What did you do? There are 2 ways that I will accept. Yep, all of those in energy level 2 add up to 7. There's another way that you remember from physical science. How else can we tell that fluorine has 7 valence electrons? Yeah, you looked in the right place. It's in group 17. I'm afraid that it's easy for you to lose track of how beautiful this is because all of this, the reason this is organized this way, meshes with, the reason this is organized this way, meshes with how we organize these, to show us all that one of the most important properties of elements is their number of valence electrons. Remember, the periodic table is arranged specifically so that we can easily tell how many valence electrons it has. And why is that so important? We talk about it a lot. Why is valence electron such an important concept? Yeah, it determines how it bonds. It determines how stable it is, and that determines how it forms bonds. And that is chemistry. How elements bond with each other, that is the definition of chemistry. So this is how we can tell how many total electrons and how many valence electrons are in here. Now, because I think you're smart, and you are smart, because I think you're smart, what would happen if instead of the atom fluorine, we had fluorine 1 minus? What does that mean? 1 more electron, so now it is 2p6. And now it is like this. Oops, definitely not like that. Like this. And why is that special? Why is fluorine 1 minus special? And why did I pick 1 minus? Why didn't I pick 8 minus or 3 plus? Why is this special? It's almost, it has 8, it satisfies the octet rule, and look at this. It's full. This is full. 2s and 2p together, energy level 2 is full. This is where it's most stable. It's most like what? This configuration, if it's not an ion, is what element's configuration? Which one specifically? You're right. It's a noble gas. It's neon. This is the exact same configuration as neon. All of this, like I said, I'm worried this will get lost on you because it's just like, oh, this is just stuff we do. But all of this meshes together, and it's like 20 different guns pointing at the same guy. All of this evidence piles together saying, this is the truth. This is the way atoms really are. Everything we do shows us that this is the way atoms behave. The easier way to do this, and this is, I don't know, maybe like not quite expert level, but this is once you get comfortable doing this, because you will have to do this, but once you get comfortable doing this, the easiest way to do it is you can use the periodic table. If it wasn't such a abominable pain, I would move the camera so that you can see. We just have to remember that I was talking about this stuff. As an example, let's do one for magnesium. Here's magnesium. You see it? Let's do this little chart for magnesium. I'm making the eraser noises with my mouse because this is a really quiet eraser. We're doing now magnesium. So I'm going to erase that. I'm going to erase this. I'm going to erase that. I'm going to erase this. How many electrons in magnesium? Let's put in 12 electrons. 1, 2, 3, 4, 5, oops, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've put in 12 electrons. I did them in the correct order after a little bit of strife. Let's write its electron configuration. 1s2, 2s2, 2p6, 3s2. 3 things. Do you see how fast I did that? It's really not that hard. If you're given the blank chart, it really is not, doesn't have to take that long. We spent a lot of time on it for fluorine because I was kind of explaining stuff, but it really doesn't take that long. Second thing, how many, well, I guess there's going to be 4 things. Second thing, Is it the right number of electrons, and how do we know? 2, 4, 10, 12. Yes, it does match. How many valence electrons does magnesium have? Good. I love this because Rhett looked here and found that 3 is the highest, and there are 2 in energy level 3. Tiana looked up there and found that it's in group 2, so it must have 2 valence electrons. So those are both, you see how that checks each other. Like, you can use that to check your work. But also, what is the ending shape here? S. What was the ending shape for fluorine?
S.
No.
P.
P. Do you notice anything special about the way this is asymmetrical? Because you've noticed it's asymmetrical before, but do you see why it might be now?
Non-metal are P.
Yeah, these aren't all nonmetals, but this chunk over here, the reason it looks like this is this chunk is called the P block. Every single one of these will end in a P. All of them. That's one way you can check. This is the S block, these 2 columns. Every one of these will end in an S. Why are there 2? Well, only 2 electrons fit in an S box. Why are there 6 in the P block? Well, 6 electrons fit in the P box. This here, can you guess? Just go on a limb. What might this be called? D. 10 electrons, so there will be 10 elements here. And this one might be the, you remember from yesterday what the next level of energy orbital is? Say it, right? You were going to say it. F. Yeah, and there are 14. So F orbitals will have 7 little boxes to fill in. So you have 3 ways to check. Is my number, my atomic number, matching the total number of electrons I had? Check. Is my valence electrons matching the number of valence electrons? Check. And is it in the right block? Check. And also, furthermore, let's do one more here. Let's do aluminum. You'll notice it's the one right after magnesium. So aluminum, atomic number 13, has how many electrons? 13. What am I going to do? Without even erasing this, how can I show aluminum now? Just add 1 more electron. Okay, and now aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. How many valence electrons does aluminum have? 3. Does that match? Yes. How many total electrons does aluminum have? 13. Does that match? 2, 4, 10, 12, 13. Yep. This says aluminum's in the P block. Is that true?
Yes.
Yes. Every element is just 1 more electron beyond the one before it. That's the easy way. I could do bismuth right here, number 83, pretty easily. Because what I would do is I would say 1s2. They all start with 1s2, and that gets me to helium. Do you see what I mean by that gets me to helium? Like 1s2 is the electron configuration of helium. 2s2 gets me to beryllium. 2p6 gets me to neon, etc., etc., etc. And that brings me to the very last thing, which is to do bismuth. There's such a thing as a noble gas notation, where I just go to the previous noble gas. Bismuth is 83, so I'd go back to xenon. This is called noble gas notation. I'm going to erase this. Noble gas notation. This is the easiest way of all. I write the noble gas in brackets of the most recent noble gas, xenon. So I would write xenon. And then I start my next line. It's always going to be an S, and the nice thing about the S's is their number is always the same as their period. 1, 2, 3, 4, 5, 6. So I'm going to start with 6S. How many can go in 6S? Any S can only have, try again, 2. 6s2 gets me to barium. Then I have F's, and the F's are always 2 behind the S. So I have 4F. How many can F have? No. We said it a second ago. No, D can have 10, 14. 4F, 14. The D's are always 1 behind. 5F, sorry, I should have said 4F, 14 gets me through lutetium. Now my D is always 1 behind, so 5D, 10 gets me through mercury. And then I'm back at 6 again, because the P's are the same as the period number. 6P, 1, 2, 3 is bismuth. And I could, listen, what makes that nice is that I don't have to fill in the alphabet diagram. which is great because I don't have enough room. I'd have to, like my outbound diagram would have to go up to here if I was going to fill in the outbound diagram. But I just use the periodic table. You will have ones on your test, and there's ones on your worksheet that you should use the outbound diagram so you can get comfortable with it. But this is kind of like the, I'm trying to think of a way in elementary school that was like this, where you learned it a really hard way first. Kind of like long division versus the shortcut kind of division. You learn it the kind of hard way first, and then there's a shortcut you can use that makes it a lot easier. The periodic table is the shortcut. The periodic table is specifically arranged to make this easy. And the super duper shortcut that I don't want you to use, that you can't use on your test, but your periodic table, maybe not yours, but this periodic table tells you the ground state electron configuration right on it. It's always the same for a given element, unless it's ionized. But I can check my work. Bismuth, you read up there. I'm going to read what this says. Xenon, 4F14, 5D10, 6S2, 6P3. Is that what I had up there? Yeah, oh, okay. Is it a different order? Yeah. I guess the order doesn't matter so much, but do you see how I'm not saying are you going to be perfect at this right now, but do you see how the periodic table can be used to do some of these? How can you get better at it? Practice. Questions or specific questions I should ask? What are your specific questions? Oh, you. Yeah, good. Aluminum has 3 valence electrons. Because both of these are 3. So even though one is S and one is P, we count them both. So this plus this is 3. Good. Thank you for the question. Other questions?